All right. Hello and good afternoon to everybody who's popping in. I see we have a flutter of concurrent viewers rolling in. Let's see. I don't really have any new announcements other than to keep your eye out for it. I'm going to be posting an announcement to Canvas. I've been working, excuse me, on exam 1, which will cover everything up to chapter 3, and I'm getting close, but I don't know yet the total problem count and all that stuff, the points distribution, etc. That should be going up on Canvas a little later today. So as I get nearer to completing writing it, I'll have more information to share with you then. And I guess the one commercial I'll throw out there is, excuse me, you can always tune into Office Hours tonight at 7 if you want to pick my brain more. By that point in the day, it'll be more. The exam will be more complete than it is right now, and so I'll have more information to share. Should you choose to join us this evening? Excuse me. In any case, let's go ahead and dive in. We are doing the final example from chapter 3, and I left off with this chemical equation, the combustion of benzene, liquid benzene with gaseous, with oxygen gas to produce water vapor. Sorry, I just said water vapor, which means that it is in the gas phase, and excuse me, carbon dioxide. And we were asked, excuse me, so sorry. Not we were asked, I asked you to try balancing this chemical equation. So, as always, the first step, I always begin by taking an atomic inventory of all the atoms on both the reactants and the product side of the reaction. You don't have to do this. Some people can just look at it and start putting in numbers and keep track of it in their head. And if you're one of those humans, more power to you. When you see me balancing chemical equations, I will always write these out because it's easy for me to lose numbers in my head, but when they're on paper, it's a little more concrete. So we have 6 carbon, 6 hydrogens, and 2 oxygen atoms on our reactant side. On our product side, we have 1 carbon, 2 hydrogen, and then 1 plus 2. We have 1 oxygen coming from water, 2 coming from carbon dioxide, and I keep those separated for a reason. All right, now we said go path of least resistance, right? Balance whatever comes easiest. And when I look at what's not balanced, carbon seems pretty straightforward. We have 6 on our reactant side, only 1. 6 on our reactant side, only 1 on our product side. To get 6 on our product side, we need to multiply CO2 by 6. We need to produce 6 carbon dioxide molecules. This will change our oxygen count in addition to balancing our carbon count. So we will have 1 plus 12 oxygen atoms and then 6 carbon atoms. So we've got 13 oxygen on the product side, only 2 on the reactant side. Again, those don't go into each other evenly, so I'm going to procrastinate and take care of hydrogen. Now 2 goes into 6 3 times, so I'm going to multiply water by 3 to balance hydrogen. This also changes, again, our oxygen count. Now we have 3 plus 12 oxygen atoms on our product side. Carbon's balanced, hydrogen's balanced, all that's left is water, and you'll notice that we have a total of 15 oxygen atoms on the product side, but only 2 on the reactant side. These 2 don't go into each other evenly, so we're going to use that technique where we apply an integer n. We need to multiply the molecule O2 by some number so that, all right, so that 2 times the number n is equal to 15, right? The total number of oxygens on our products side. Now we divide both sides by 2 to find what that number is, and it turns out that number is 15 halves. So when we go back, when we go back to our original reaction and we punch that number in, two times 15 over 2 is equal to 15, right? So as of right now, our reaction is balanced. However, you can never leave a fraction in as a stoichiometric coefficient in your balanced chemical equation, all right? That can never happen. You can use a fraction to balance it, but you've got to you've got to get rid of that denominator, once you are out the other end. So what you do to get rid of your fraction that you just introduced is multiply everything in that balanced chemical equation by your denominator, all right? So when we do that, we will come up with our final answer of 2 molecules of benzene plus 15 molecules of oxygen. Oh, sorry, benzene's a liquid, oxygen's a gas. And this will produce 6 molecules of water vapor. Oh, and I just saw that I forgot my CO2. Plus 2 times 6 is 12. 12 molecules of carbon dioxide gas. So that is the balanced chemical equation. Sorry, I'm getting a phone call from Vineland, New Jersey. I don't know what that is, but my guess is it's a telemarketer. This is our final answer. And again, you can expect to see a whole range of balancing chemical equations problems on exam 1. Some that'll be very straightforward. Others that will require a little more work. And then some, like this problem, that will require you to use a fraction to balance and then get rid of the fraction as the last step of the problem. All right, so that is our introduction and hopefully our review of balancing chemical equations. And with that concluded, we are ready to dive in to chapter 4. All right, now chapter 4, as I said in the description, is a favorite of mine. In chapter 4 is all about solution chemistry. All right, solution chemistry. It's chemistry that happens in solution, where we have our reactants are dissolved in some sort of solvent, usually, because this is Gen Chem, usually water. And this is will be our first look at actual chemical reactions, how compounds react with each other, interact with each other, and change. It really is kind of like our first stab at the beating heart of chemistry, and I'm psyched for this. All right. One thing that I want to say though before, so where this is all headed. Chapter 4 is headed into an in-depth look into solution chemistry, and we'll be looking at 3 reaction types. We'll be looking at precipitation reactions, acid-base reactions, and redox reactions. All right. But before we can get to those, we kind of need to do what's the word I'm looking for? We need to lay a foundation. Before we start talking about reactions, we need to kind of explore these chemical equations that we have reviewed balancing and how the reactants and products all relate to each other. And so before we can dive in and actually start talking about the solution phase, first we are going to have to review the subject of stoichiometry. All right, and this is where streaming classes to YouTube, where I missed some of the sensory feedback that I used to get in the class. Usually, when I say the word stoichiometry, there would be a collective groan, because most students don't like this word. And if you don't remember exactly what this is, and you kind of have this vague sense of like, I remember not liking it, but I don't know why or what. Stoichiometry has to do with your unit conversions going back and forth between grams and moles. All right, and so balanced chemical equations, starting with so many grams of reactant, finding grams of product, that sort of thing. All that is stoichiometry. And again, this would have been covered. It was covered in your prerequisite courses, but because it is so central to everything that we're going to do in the future, I'm going to invest the time in a review, because everything moving forward pretty much will relate to stoichiometry. That being said, with me saying everything we're doing from here on out will really relate to this more or less, that is your signal that this is the thing that you want to get good at. And I'm taking the time to review it. And if you struggled with this in the past, really, really dig in deep. Your ability to do well in this course hinges on your comprehension of this material. So shove all the other stuff to the side and focus in hard. All right. So let's talk about stoichiometry. Let's begin by looking at a familiar chemical equation. The combustion of hydrogen gas to produce water vapor. All right, now this equation as written is not balanced. I'm just going to balance it quickly for us here. You add a 2 in front of hydrogen and water, and the equation is now balanced. Same number of atoms on both sides of the equation. Now, I'm also going to add a 1 in here for the stoichiometric coefficient of oxygen. You don't have to, and you actually, whenever there's 1 mole of of any reactant, any or product, molecule, atom, what have you, you typically don't write the 1, but I'm gonna write the 1 in here for emphasis sake. All right, to emphasize something. Now, one way to read this, there's more than one way to read a chemical equation. All right, you could read this chemical equation. One of the ways you could read it is you could read 2 molecules of hydrogen react with 1 molecule of oxygen. Right, ... to produce 2 molecules of water. That's one way to read this. But another way to read it, and even a more accurate way to read this balanced chemical reaction, would be like so. You could read it like this: 2 moles of hydrogen react with 1 mole of oxygen, ... All right, that is another totally valid way to read it, and it's even a better, I consider it a better way to read it, because, and this is the take home, your stoichiometric coefficients which, again, by way of reminder, are these guys. They're the big numbers out in front that tell you how many of each are present. Your stoichiometric coefficients are molar ratios. All right. They represent ratios of the moles of every reactant and product of a chemical equation. All right. These are molar ratios. And here's what that allows us to do. All right. Actually, forgot to write my reaction out in a separate layer. Let me recreate this real quick. All right. That knowledge that these stoichiometric coefficients represent molar ratios allows us to solve a litany of problems, a ton of different types of problems. We can use this knowledge to solve. So, for example, let's do our first example here. If I told you that 0.112 moles of H2 react completely. I could ask you, I could ask you I could ask you how many moles of water are produced. All right? I could ask you that, and here's how you'd solve that problem. You're given that you have 0.112 moles of hydrogen, and you want to know how many moles of water are produced. Well, what you need is a unit conversion, one that converts moles of hydrogen to moles of water. And that unit conversion comes straight out of the balanced chemical equation. Our balanced chemical equation tells us 2 moles of hydrogen produce 2 moles of water. So that ratio is a 2-to-2 or a 1-to-1 ratio. All right, you get any mole-to-mole conversion, you get that out of a balanced chemical equation. So moles of hydrogen cancel, and when you multiply 0.112 by 2 and divide by 2, you find that 0.112 moles of water are produced. All right? Excuse me. It's a very sharp intake of breath. That is not the only question that we can ask with this problem. All right? I could have also asked you, I could have told you that you got 0.112 moles of hydrogen that react completely. I could have asked you, and I'll ask you now, to determine how many moles of oxygen are consumed. And the way you solve this problem, you may be going, whoa. But oxygen's a reactant, not a product. It doesn't matter. The way you solve this problem is exactly the same as the way we solved the previous one. So we're told that 0.112 moles of hydrogen react completely. And we want to know how many moles of oxygen are consumed, right? How many moles of oxygen react with it? So we need to put moles of hydrogen in the denominator, moles of oxygen in the numerator, all right? And here, just like before, the balanced chemical equation will give us the ratio. It tells us 2 moles of hydrogen react with 1 mole of oxygen, and those are the numbers we plug in here. 2 moles of oxygen, 1 mole of oxygen, 2 moles of hydrogen. Moles of hydrogen cancel, And when you cut, I'm not going to do it in my head just because I'm bad at math, in my head at least. When I punch this into my calculator, the answer that I'm given is 0.056. All right? But you always have to ask yourself, how many sig figs should you have? And when you look at it, we start with 3 sig figs, but 0.056 only has 2, so we need to add a 0 for our answer to be correct. 0.0560 moles of oxygen are consumed. And that is our answer. All right? So the balanced chemical equation gives you the molar ratio, allowing you to convert between any reactant or product with any other reactant or product, right? It tells you the relationship of consumption and production, depending upon whether you're looking at the reactant side. Reactants are consumed, products are produced for specific chemical equations, all right? And it'll always be relative. It'll change reaction to reaction, which is why you always are going to start these problems by balancing a chemical equation. All right, now let's, you know what? I thought I was done with this reaction, but I'm not. Those 2 examples that I just provided are too easy to ever put on an exam. And again, chapter 4 material will be on exam 2, not exam 1, so this is not on the one that's coming at you. But for exam 2, I would never put something that soft on an exam. What's far more photorealistic for what you'll see out there in the wild is an example like the following. Actually, I'm just going to move my chemical equation over a little bit so I can move this example up. All right. So consider the following example. Oops. There we go. If 1.0 grams of hydrogen reacts completely how many grams of water are produced? All right, now here is the critical thing to remember whenever you're doing a stoichiometry problem. These stoichiometric coefficients are molar ratios. It's super tempting to want to say, oh, we got 1 gram of hydrogen, right? 1 gram of hydrogen. I can see from my reaction that it's a 1-to-1 ratio between hydrogen and water. So if we have 1 gram of hydrogen, we're going to make 1 gram of water. That is not the case, because these are not mass ratios. They are molar ratios. And so before you can use them, before you can use your balanced chemical equation to convert from hydrogen to water, you first must convert grams of H2 to moles of H2, and then you can do your mole to mole conversion. All right, so don't make that mistake. All right, let's do this. So we have 1.0 grams of hydrogen, and we need a unit conversion that will cancel grams of H2 and leave us, with moles of H2. All right. Now we're going to have to calculate our molecular weight here. 1 atom of hydrogen has a mass of 1.008 AMU. And here we have two of them, right? So we've got to add these two together. Right, so H2 will have a molecular weight of 2.016 AMU. 2.016 grams of hydrogen are in 1 mole of hydrogen. And now, grams of hydrogen cancel grams of hydrogen. Sorry, the more I mess with this, the more it just looks like 2016. Which was not as bad a year as people said it was, especially relative to 2020, right? Okay, so we've converted now from grams to moles. Before we crunch our numbers, we're not done because we don't want to find moles of hydrogen. We want to find grams of water. So we're gonna take this to the next unit conversion and convert from moles of H2 to moles of H2O. And again, these numbers come directly out of our balanced chemical equation. Now, moles of hydrogen cancel moles of hydrogen, and we're ready to move on to our final unit conversion. All right, we're going to put moles of water in our denominator because we want that to cancel. And we want to find grams of water. And to do this, we need to calculate the atomic mass, right? Not the atomic mass, the molecular mass. Hydrogen is 0.008, oxygen is 16.00, but we do have two H's present, so the molecular weight of water will be 18.016. Sig figs wise, using the numbers that I used, we'd have to, the last significant digit in this number is in the first decimal place. However, we always wait to round till the end of the calculation. So I'm going to put a line here reminding me that this molecular mass only has 4 sig figs. But I'm going to wait to round it till the end of the calculation. All right, moles of water cancel moles of water. And now we're ready to crunch our numbers. We have 1 divided by 2.016 times 2 divided by 2 times 18.016 comes out to be, my value here is 8.9365. All right. When I look at sig figs, I have 4 sig figs for my molecular mass, and I have 4 sig figs for my molecular mass of hydrogen as well, but my initial mass only has 2 significant figures, so my answer can only have 2. So I count off my first 2 sig figs, see that 3 rounds down, and so my final answer with the correct value, units, and sig figs will be 8.9 grams of water as my final correct answer. All right. And again, just drawing your attention, 1 gram of hydrogen produced almost 9 grams of water. So the 1-to-1 ratio that you see in the balanced chemical equation is a molar ratio, but clearly it is not a mass ratio. All right. The last thing that I have to say here is this number has a name. This is called your theoretical yield. All right, this is your theoretical yield. And you may be wondering, wait a minute, why are you calling this theoretical? Shouldn't we produce 8.9 grams of water if 1.0 grams of hydrogen react completely? And the answer is yes, you should, but you don't always. All right, you should, but you don't always. The theoretical yield is what you should produce based on what you start with. All right, this is what you should produce. The actual yield is what you do produce. All right, what you should produce is your theoretical. What you do produce is your actual. And then there's something called a percent yield. And percent yield is equal to your actual yield divided by your theoretical times 100. It's a percentage of what you actually made over what you should have made, right? What you should have made. We always get our theoretical yields are on paper, right? In a world without errors, in a world with no mistakes, in a world where reactions are completely efficient. Not every chemical reaction is an efficient reaction. Some reactions are sluggish, some are messy, some make more than one thing, some have byproducts. Your actual yield is what you get in the lab. And your percent yield is a sort of, it rates the reaction efficiency and the experimental technique. Of the person doing the reaction. All right, the percent yield, there's two reasons why percent yields are low. One, it could be the reaction you're doing doesn't want to happen, right? It could be that your reactants decompose as fast as they do the productive reaction, so you're losing a lot of material to side reactions. Some reactions are just inefficient. It also could be that the person doing the reaction sucks, right? You could take a reaction that's very efficient, but maybe you're dealing with a sloppy chemist who's spilling stuff, who's losing material, who's not careful all the way through, maybe doesn't clean their glassware. And so that's a reason why percent yields can be low as well. So it's kind of a mashup of these two things together. All right. Now let's take this information. Let's take this information and apply it to an example. All right, so let's work an example together. Iron 3 oxide, and this is, by the way, exam caliber. Again, not for exam 1, because it only covers through chapter 3. This would be an exam caliber 1 for our second exam, exam 2. Iron 3 oxide reacts with aluminum metal to produce aluminum oxide and iron metal. All right. Part A is write a balanced chemical equation. Part B, what is the theoretical yield of iron metal if 5.00 grams of iron 3 oxide reacts completely? Question mark. And then part C, determine the percent yield of iron metal. Determine the percent yield of iron metal if the actual yield is 3.32 grams. All right. Okay, so this is exam caliber. Like I said, the problems that we started with, the example problems we started with, were purposefully soft to kind of introduce the topic, but this is full metal chemistry. So here's the great thing. This is a great test of your metal. If you know how to solve this problem, you are a step ahead of the game. If you don't know how, that's why I'm going to do it step by step. And you also know what to practice. So either way, you're walking away with something good, with useful information. All right, now let's go ahead and tackle the first part of this problem, which is balancing our chemical equation. We're told that we're dealing here with iron 3 oxide. Well, we know that the iron cation in this compound has a charge of +3 because we're told oxygen is the atom, as an anion, it's oxide. We can figure out its charge from the periodic table is a -2. And so we know that whenever we're dealing with a cation and an anion whose charges don't go into each other evenly, we swap them, right? So iron, we give the cation the subscript of the anionic charge, and we give the anion a subscript equal to the cationic charge. So iron 3 oxide will be Fe2O3. Now, we're told that here we're also dealing with aluminum metal. Anytime you see that aluminum metal or iron metal on the product side, that means you're just dealing with that metallic element by itself. So this is just going to be plus aluminum, actually. Oops. There we go. So this is just going to be plus Al. All right. And this produces aluminum oxide. Now we know the charge for oxide. We do not yet know the charge of aluminum, but when you look at the periodic table, you see aluminum has 13 electrons. Its nearest noble gas, neon, has 10. So it has to lose 3. It will also have a cationic charge of +3. So we're actually dealing with aluminum oxide the same sort of scenario that we dealt with iron 3 oxide. Aluminum will take the anionic charge as its subscript, and oxygen will take the cationic charge as its subscript. The final product is just iron metal, so we write Fe by itself. All right, now that was a bit of heavy lifting. We had to draw on, you'll notice, our knowledge of naming to get our reactants and our products out, but we're still not balanced here. We've just written our reactants and our products. It can be very easy to feel like a little bit mentally tired at this point. You're like, glad that was over. What's part B? But remember, it's not enough to write your reactants and products. You also need to take that chemical inventory and make sure that everything is balanced. All right. So we have on our reactant side 2 iron atoms, 3 oxygen atoms, 1 aluminum atom. On our product side, we have 2 aluminum atoms, 3 oxygen atoms, 1 iron atom. All right, this is going to be easy enough to balance. We need 2 iron on our product side, so we multiply Fe by 2. We also need 2 aluminum atoms on our reactant side, so we multiply Al by 2 as well. And so this is our balanced chemical equation. And we will be using this to solve the remainder of the problem. All right, we've done part A, we've balanced it. Part B, we need to determine the theoretical yield, how many grams of iron from our 5.00 grams of iron 3 oxide that react completely, right? So, actually, hang on. I keep mismanaging my layers here. So we have 5 grams of iron 3 oxide. We need to find our grams of iron. All right. So we start off, this is just like with our previous theoretical yield calculation. We want to use the balanced chemical equation that we have with its mole-to-mole ratio between iron 3 oxide and iron metal. You can see it's a 1:3 ratio. But again, that is a molar ratio. We need to begin by converting our grams of iron 3 oxide to moles. Okay, sorry. Kate and Kyle, I just saw your questions. And I'm actually so glad you noticed that that the phase symbols weren't included in this problem. You only have to worry about phase symbols when they're given to you. So in this problem, I didn't tell you what phase each molecule or element had. And so because I didn't tell you, you have no way of knowing. So if you're not given phase symbols, don't worry about it. If you are given phase symbols, then you always want to include them as part of your answer. But because I wanted the focus to be on the stoichiometry, I left them out for this problem. And you'll find, actually, at the beginning of the semester, phase symbols aren't super important, but as we move on, and even in this chapter, they'll start to become more important. And then as we get deeper into the course, their significance will become more prominent. But if you're not given them, don't even trip. All right, excellent questions. Sorry, I just now saw them. I don't know when you posted them. Hope you weren't waiting too long. So, we need to convert from grams of iron 3 oxide to moles. And so we need to check out consult our local periodic table, which I have down here. Iron is 55 something. 55.85. Oxygen is 16.00, and we have 3 oxygen atoms and 2 iron atoms. All right, so 3 times 16 is 48. 55.85 times 2 is 111.70. So that plus 48 will give us a molecular mass of 159.70. Again, because we're doing addition here, you have to pay attention to precision, and it actually adds to a perfect 159.7, but because there's that 0 there, or because each of the numbers we added is precise to the second decimal place, we have to add a 0 to give it the correct number of sig figs. So 159.70 is the molecular mass of iron 3 oxide. Now grams of iron 3 oxide cancel. In our next unit conversion, we have to convert from moles of iron 3 oxide to moles of iron atoms. All right, and we get this ratio straight out of the balanced chemical equation. 1 mole of iron 3 oxide produces 2 iron atoms. Now moles of iron 3 oxide cancel. Finally, we can convert from moles of iron to grams of iron, and because this is just iron atoms, we get to use the atomic mass. 55.85 grams of iron are in 1 mole, and now we're ready to crunch our numbers. So 5.00 divided by 159.70 times 2 times 55.85 comes out to be, so this is a long number, 3.49718.222. All right, that is the value. How many sig figs can I have? Well, the atomic mass of iron has 4. The molecular mass of iron 3 oxide has 5, but my initial mass only has 3, and so that is going to limit me. So I count off my first 3. 7 will round up. When you round 7 up, that 9 rounds to a 10. So this is 3.5 after rounding. The problem is this only has 2 sig figs, and I need 3. So we've got to add a 0 here to get the correct number of significant figures. Then we add our units, grams of iron, and that is my correct answer, the correct units, and the correct sig figs. This is the answer for part B. This is our theoretical yield. All right. Part C, the final step of this problem, is we're given our actual yield and we're asked to calculate our percent yield. We know that the percent yield is equal to actual over theoretical. And we're told the actual yield for this problem, which I'm actually just scrubbing back through to pull it out because there we go. The actual yield is 3.32 grams. And the theoretical we just found out was 3.50 grams times 100. I actually forgot to write that in over here. All right, so let's crunch our numbers. 3.32 divided by 3.50 times 100. So our value is 94.8571429. But again, my actual yield and my theoretical yield both have 3 sig figs. So my answer must have 3 sig figs. So I count out my first 3. 5 is going to round up. So this is 94.9%. All right. So that is the answer to part C. That is our theoretical yield of iron 3 oxide. All right. Let's see how we're doing. Okay, so that was a long problem. And again, check out the assigned homework out of the TRO textbook. Again, it's not for credit. This is just for your practice. If you want to see more theoretical yield calculations, you want this to become like breathing. Definitely way ahead of exam 2. Let's go ahead and look at a new type of problem. All right. So at this point in time, hopefully, if I give you a reaction and a quantity, an initial quantity of a reactant or a product, you could tell me, you could figure out the theoretical yield, right? You could roll through the calculation. We've done 2 of them already today. Hopefully, after getting those 2 reps in, you have enough information to bust one of those out. What we haven't seen yet at this point in time is a problem like the following. All right, so let's do an example. I'm going to, for the sake of time, so we can focus in on kind of the new aspect, I'm going to write out this balanced chemical equation. Plus it's a reaction that we've already balanced before. 3 moles of hydrogen gas react with 1 mole of nitrogen gas to produce 2 moles of ammonia. All right. Now, here's what makes this problem different. Let's say that we mix 1.679 grams of hydrogen together with 2.780 grams of nitrogen, and I ask you to find the theoretical yield of ammonia in grams. This is a different kind of problem. In the examples that we've done up to this moment in time, I'll give you a mass of 1 reactant and I'll say, this reacts completely. How many grams of products do you make? And you could do it. But the question here is, do you use the mass of hydrogen or do you use the mass of nitrogen? Which one do you use to calculate your theoretical yield? And the answer to that question is you use the reactant that runs out first. All right? You use the reactant that runs out first. And you may be going, what am I talking about? What am I talking about? And here's what I'm talking about. All right, so here's the deal. Let's say you're eating chips and salsa. All right, you're engaging in the act of consuming chips and salsa. So you're dipping your chips into salsa and eating them, right? If you do this long enough, one of two things are going to happen. All right, either you will run out of chips and you'll be left with a bowl with some salsa in it and you'll be sad, or you will run out of salsa and you'll just have a bag of the leftover chips and you'll be sad. Whichever one of those happens, either way, when one of those two runs out, you're done eating chips and salsa, right? At that point, your only options are drink the salsa or just eat the dry bag of chips, right? One will dry out your mouth. The other one will burn your esophagus, depending upon how hot you like your salsa, not how you hot your salsa. Dyslexia makes life more fun, right? More interesting, at least. So you're done eating chips and salsa when the chips run out or the salsa runs out. And in this type of problem, you're given a quantity of chips and you're given a quantity of salsa, and you need to figure out which one will run out first, because the reactant that runs out first will limit the amount of product the reaction makes, that the reaction produces. All right, the one that runs out first limits the amount the reaction makes and is therefore called the limiting reactant. All right, the limiting reactant. Now you may be sitting there wondering, okay, well, I get it. I get the concept. I get the chips and salsa analogy. How do we determine which one runs out first? What you need to do is you need to carry out the calculation that we've been doing for theoretical yield twice. Do it once for hydrogen, do it once for nitrogen, and whichever value gives you a smaller theoretical yield in grams, that is your true theoretical yield, and it came from the limiting reactant. So this may seem like conceptually a lot weightier, a lot harder, a gnarlier problem, but it's the exact same calculation, just twice. It's the same thing, you're just doing it in duplicate. All right, so it's not the end of the world that it first looked like. Let's actually get down to business and defeat the Huns. All right, let's start by doing the calculation first for hydrogen, then for nitrogen, and we will compare the two to determine the limiting reactant and the theoretical yield. So first, we need to convert grams of H2 to moles. All right, grams of H2 to moles of H2. We use the molecular mass of hydrogen, which is 2.016 grams of hydrogen per mole. Grams cancel grams. We're left with moles, which is good. Step 2, we need to convert from moles of hydrogen to moles of ammonia, NH3, and this comes straight out of our balanced chemical equation. 3 moles of hydrogen produce 2 moles of ammonia. Moles of hydrogen cancel. The final step, the final unit conversion we need, is the unit conversion that will take us from moles of NH3 to grams of NH3. And here we need to calculate our molecular weight. All right. Nitrogen has an atomic mass of 14.01. Hydrogen has an atomic mass of 1.008. We've got to multiply this by 3. All right, so it's time to crunch some numbers. 1.008 times 3 plus 14.01 comes out to be 17.034. Precision-wise, sig figs-wise, we're limited to the second decimal place. So I'm going to put a line there to remind myself that this molecular weight has 4 sig figs. All right. And moles of nitrogen cancel moles of nitrogen. Whoops. I need to rewrite that, sorry. With my sig figs. And now moles of nitrogen, or sorry, moles of ammonia cancel moles of ammonia. And we're ready to crunch our numbers. So 1.679 divided by 2.016 times 2 divided by 3 times 17.034 comes out to be let's see, we can keep 4 sig figs here because both of our atomic masses, or sorry, molecular masses have 4. And our initial mass also has 4. So all the numbers we use have 4 sig figs, so we can keep 4 of these guys. So this will be 9.458 grams of ammonia. And again, this might be our answer, but I don't know. And you don't know yet. Before we can determine that, we need to do the same calculation starting with our mass of nitrogen, right, which is 2.780 grams. And then we have to compare. Whichever one is lower is the theoretical yield, and it came from the reactant that ran out first, i.e. the limiting reactant. So we need a unit conversion that'll convert grams of N2 to moles of N2. And the atomic mass of nitrogen is 14.01, so the molecular mass would be 28.02, because there's 2 nitrogen atoms in 1 molecule of nitrogen. Grams here cancels. Angelina, excellent question. You absolutely can. Angelina's question was, could you could you just do these calculations twice to find moles of ammonia and then find grams out the other end? You totally, and then once you know the moles of your theoretical yield, convert to grams after you do that. You totally can. That is 100% correct. And your answers will be the same. So, absolutely. And if you prefer to do it that way, totally go for it. Moles of N2. So we got to convert from moles of N2 to moles of NH3. And here we can see that 1 mole of nitrogen produces 2 moles of ammonia. So now moles of nitrogen cancel, and we're left with moles of ammonia. Now the cool thing is, for this next unit conversion to go from moles of ammonia to grams, we actually have already calculated this atomic mass in the step before. So we just have to, sorry, I said atomic mass, this molecular mass, we just have to plug in the molecular mass above. For NH3, again, reminding ourselves that we have 1, 2, 3, 4 sig figs here. Moles of ammonia cancel moles of ammonia. And now we're ready to crunch our numbers. So 2.780 divided by 28.02 times 2 times 17.034. All right, this is 3.380, again, 4 sig figs, grams of ammonia. Now, once you have these down, you look at the two numbers, and you can see that the mass of ammonia that we get from our initial quantity of nitrogen is smaller. So we would say that the limiting reagent, Lr, is nitrogen, and the theoretical yield is 3.380 grams of ammonia. All right? That is our solution to this problem. Thanks, Jamal. So this is the answer to this problem. One thing I want to point out is I kind of stacked the odds for this problem to be, to purposefully draw your attention to something. One, we framed this by saying we want to find out which reactant is going to run out first. And you can't do that if you're just looking at the mass in isolation, right? Hydrogen actually had a smaller initial mass than nitrogen, and yet nitrogen still ran out first. That's often one place students go where they're like, oh, I should just see which one has less. The amount in grams doesn't always, sometimes it will tell you the theoretical, it doesn't tell you the theoretical yield. Sometimes the smaller mass amount will belong to the limiting reactant, but in this case, the larger mass amount actually belonged to the limiting reactant. It's a combination. What determines your limiting reactant is a combination of the initial mass, the molecular mass, and the stoichiometric ratios, the mole-to-mole ratio between each reactant and the product. And those three together are what determine the theoretical yield. So you can't just look at grams. You can't just look at moles of reactant. You have to look at everything entirety. So either calculate the moles of your product twice or the mass of your product twice. That is the only surefire way to determine your limiting reactant. All right. All right, now I want to leave us. So that was a big, gnarly problem. I want to leave you with the gnarliest example yet. All right. I want to leave on a high point with a challenge. And this is the example that we will pick up our discussion on Monday. So next week we're going to open lecture with this problem. What I'm going to do here is I'm going to give you the example. I'm going to write it all out. This is full metal exam caliber. Give this a try. In your free time, as you're looking to study, students are always like, are there problems? Are there examples that would be good? Look to the book, look to the assigned homework, but also give this one a try. We haven't gone over how to name acids yet. That'll be coming a little later this chapter, so I'm just going to tell you HBr reacts with sodium carbonate to produce sodium bromide, not bromine, bromide, carbon dioxide, and